Okay. So good morning. Uh, we are going to the presentation now. So hope all of you can see the screen. If you have any doubts or something, you can interrupt me and ask. Your chats may not be visible to me now. Okay. So coming to the new um, subject, the digital signal processing, which is the continuation of the subject that we have seen in last class, the signals and systems. We can consider it as an elder brother of signals and systems. Uh, so, the prerequisite for this course is signals and systems. Now, DSP, the short form of digital signal processing is DSP. Question is, why do you go for DSP? What is the importance of DSP? What is the relevance of DSP? So, uh, if you see any mobile phones which are available, there will be at least one processor or one core which is a DSP core. So this is mainly for processing the audio signals, which will be done by for processing the signals. You need some DSP processors. Um, so, what is the difference between a DSP processor and normal processor? So if you consider a normal processor, say if you consider a processor like 1 minute, I will take some. So I have to so take. If you consider some normal processor, if you consider the say memory allocation, all the programs that are to be executed, they will reside in this location. All the data, everything will be in the same memory location. So when you are accessing some programs, say for example, add some location, say register 1, contents of register 1 and register 2, this program may be written somewhere inside this. So when you execute this program, you need to take data corresponding to R1 and R2, which will be also in the same memory location. So when you have both in program and data in same memory location, when you access program, you won't be able to access data. So that's one problem of normal processors. But when you have program and data in different memory locations, say, like this, these are the programs, these are the data. When you have them in different locations, when you add R1 and R2, which is a program sequence written in this memory location, and R1 and R2 will be stored in the data location. So while you access the programs, you will be able to access data also. So this kind of architecture has the advantage that while accessing program, at the same time you can access the data, and this increase the speed of the processing. So The architecture corresponding to this are called von Neumann architecture and Harvard architecture. Uh, von Neumann architecture and Harvard architecture. So normal process have this kind of architecture, von Neumann architecture, and this is the Harvard architecture, and that's for DSP processors. And since this kind of architecture has its own advantages, they are used in DSP process, and DSP processors are used for processing the audio signal in mobile phones, and almost all mobile phone have DSP cores. So this is the importance of DSP processor. Yeah. Now it has applications in audio, speech, image, and other signal processing, biomedical signal processing. Any signal you take, it has DSP has some application in that. Now you take the processing of signals. How do you process signals? You need some filtering. You may there are several processes. So these processes become easy in digital domain, and you need very much lesser electronic components um, when you use DSP processors. So we shall see how and what it is. Now, yeah. Now, what is DSP filter? I hope that all of you are able to see me and hear the presentation. Can one of you just unmute your mic and tell something? You're able to hear and see this lecturing properly, right? What?
Yes.
Okay. So, yeah, what is basically a DSP filter? So let us see what is a filter. Okay, suppose you have some let us take a transfer function h z equal to 1 plus z inverse, h z equal to 1 plus z inverse. Yeah, what is this basically? H z equal to 1 plus z inverse. If you have, if you write this as yz, or hz as yz by xz, is 1 plus z inverse. So basically yz is from this you can write as yz as xz plus xz into z inverse. Okay, just if you take the inverse transform, this become yn equal to xn plus, what is inverse transform of xz into z inverse? It is xn minus 1. So the output yn is xn plus a delayed version of xn. So your yn, if you take say y0, or if you take y1 is x1 plus x0. You take the two sequences of x, that is a zeroth sequence and first sequence, and add them together, then you get the present sequence of y. That is the output. So that means if you have say signal thing like this, if this is xn, and you have here what happened? 0 and 1. Suppose you have some value, say 2 and 3. Y of 1 will be x of 0 plus x of 1, which is h of 0 plus x of 1, which is 2 plus 3. Okay, so like that you can. So y of 1 is 5. So basically hz equal to 1 plus z inverse is a transfer function of a filter. Now what kind of, I think we have already seen this, what kind of filter it is. Let us just once more see what it is. Let us see the instead of z, let us write it as z is basically r e raised to omega. So if r is equal to 1, it becomes discrete time for a transform, and this you can write as h e raised to j omega when r become 1. Z is r e raised to omega. So h e raised to omega is 1 plus e raised to minus j omega. Now in this, if you take e raised to minus j omega by 2 outside, this become e raised to j omega by 2 plus e raised to minus j omega by 2. Now this you can write as e raised to minus j omega by 2 into this is basically e raised to omega by 2 plus e raised to minus j omega by 2 is cos omega 2 cos omega by 2. So this whole thing become 2 cos omega by 2. Now if you take the magnitude of this, magnitude of h e raised to omega, this become the magnitude of this e raised to minus j omega by 2 into magnitude of 2 cos omega by 2. This is a mode of a into b, which you can write as mode a into mode b. So this become e raised to minus j omega by 2 modulus into modulus of 2 cos omega by 2. Now if you see this, this is basically what is mode e raised to j theta. You consider mode e raised to j theta. Mode e raised to j theta is basically mode of cos theta plus j sin theta. What is this? Root of cos square theta plus sin square theta. Cos square theta plus sin square theta, which is basically 1. So this become 1. So this you can write as 1 into 2 cos omega by 2 modulus of that. Now if you plot this for different values of omega, say starting from 0 to pi, how will be the plot? If you see the plot, you can see that the plot will be you give omega equal to 0, this become 2 cos 0, which is 2, is having magnitude, highest magnitude, and omega equal to say pi by 2, this become cos pi by 4, 1 by root 2, 2 into 1 by root 2 become root 2. So you get, here you have 2, here you have say 1.4, which is root 2. This is for omega equal to pi by 2. Omega equal to pi, similarly you get 2 cos pi by 2. So when you reach pi, 2 cos pi by 2 is 0, so it goes to 0 value. So it's basically a low pass filter. To consider from 0 to pi, and at the negative frequency, angular frequency region, you will get the same thing this side also. So you are concerned only about the positive frequencies. So from 0 to pi, you can see that this is a low pass filter and it's of first order. This is a first order low pass filter. So this way we can design a digital filter. So how will you implement this kind of digital filter? What does this 1 plus z inverse means? Or you know that 1 plus z inverse, h z equal to 1 plus z inverse means that it is yn equal to xn plus xn minus 1. Yn equal to xn plus xn minus 1. So when you have some signal coming in, say when you have some signal coming in, suppose this is xn, this xn, and you need xn minus 1 also. Xn plus xn minus 1 is yn. So you have xn is coming here. You add it with say some xn minus 1 also. So how will you get xn minus 1? Xn, you take some, you add this together here. You take xn. How do you get xn minus 1? You take a delayed version. You can get xn minus 1 from this. Take a delay. Delay is represented by z inverse. Then that thing you can take from here, and if you have a delay like this will be xn minus 1. And if you add them, you get yn. So you can take yn here. There are several ways in which you can represent it. Other way of representing it is you can represent it like this also. Xn is here. This you give directly. Xn minus 1, you can get a delayed version from here, z inverse. Add it here. So this is xn. Xn goes here, you get xn here. And xn minus 1 you can get from here. You add it to get y of n. So how will you implement this delay? You can use some delay, say delay flip-flop or whatever it is. You can, if you have some delay, you can implement this in hardware. So addition also you can implement. So this way you can implement a first order digital filter. Yeah. Now, all of you remember what is discrete time Fourier transform, right? When you have hz equal to say 1 plus 3 z inverse plus 9 z raised to minus 2. If you have hz like this, what is discrete time Fourier transform? You replace z with e raised to omega, r equal to 1. When r equal to 1, z transform become discrete time Fourier transform. So you have h e raised to j omega. This is equal to 1 plus 3 e raised to minus j omega plus 9 e raised to minus 2 j omega. Okay. So this is the discrete time Fourier transform or the frequency response of hz. Now, how will you represent it in, say, suppose you have some signal xn, you can find where you will find the z transform xz. So to find xz, use the formula xn equal to xz. What is the xz formula? Xz is sigma xn that raised to minus n, or n where is from 0 to infinity if the signal is a causal signal. So xz is like this. Now what is discrete time Fourier transform? It is x e raised to omega. You replace 0 to infinity xn, replace z with e raised to minus j omega, so this become e raised to minus j omega. Replace z with, z is basically r e raised to j omega. So when r become 1, this become e raised to j omega. So this is the DTFT, discrete time Fourier transform. Now your signal is xn, which is a discrete signal. If you have a discrete signal, can you tell something about the frequency domain representation? If something is discrete in one domain, what happened to the same thing in the other domain? You can unmute and tell. One of you can unmute and tell. If a signal is discrete in one domain, what happens in the other domain?
Periodic.
Definitely, it is periodic in the other domain. So x e raised to j omega, which is the frequency domain representation of xn, will be a periodic signal. So if it is a periodic signal, so let us represent one periodic signal. Suppose it is like this, a periodic signal like this. So if it is a periodic signal, not all the portions of the signal is relevant to us, right? Not all the portions of the signal is relevant to us. We need to consider only the portion which is, say suppose it is repeating from this to this. We are concerned only about this because we know that this same thing is repeating. So this is something which we are concerned about. Now we know that if you have a continuous signal, we don't need all the signal or all the continuous portion of this. That's how we came to the sampling, right? So similar to that, we don't need all the values. We are not concerned about all the values in this discrete time Fourier transform. So we'll take small samples at a convenient sampling. You conveniently sample it. We take all these definite values. Okay. Then suppose you take, say, n values. N values from a single period. If you take it like this, what you're going to get is a set of values which is called the endpoint DFT. Endpoint DFT of the signal xn. Of the signal xn. Is that clear? So we are taking endpoint DFT of the signal xn. So these values forms the values of the endpoint DFT. Is that clear? Okay. So now endpoint DFT, which is also called discrete Fourier transform. So discrete time Fourier transform is the frequency domain representation of xn. We know that xn is discrete, so a discrete time Fourier transform will be periodic. So we just need one period. So take one period, and in one period also you don't need all the continuous value. You sample it, or you just take some samples. So those samples become the endpoint. If you take n samples, it become endpoint discrete Fourier transform. So from the discrete time Fourier transform, the time disappears and discrete Fourier become discrete Fourier transform. So DFT is now, it is not periodic. DFT is not periodic. DFT is not continuous. It is discrete. So it is a discrete and continuous. Now coming back, So how will you represent your discrete, so the discrete time for a transform equation is x e raised to omega equal to sigma xn e raised to minus j omega, and since omega is 2 pi by n, you can write this as this can be written as sigma n equal to 0 to infinity xn e raised to minus j 2 pi by n. Omega you can write as 2 pi by n into n. So this is a discrete time for a transform. And what happens if you take limited number of samples? So this is x e raised to j omega. This is the equation for discrete time for a transform. This is the equation for discrete time for a transform. And x e raised to omega is a periodic signal. Say suppose the signal is like this in one period. Suppose you take n samples like this, 0 to n minus 1 samples. Then what you are going to get is this x e raised to omega is periodic. Then this periodic signal become discrete and a periodic signal. Remember, discrete time for a transform is continuous as well as periodic. So discrete Fourier transform is a periodic as well as discrete. So we normally represent discrete Fourier transform as xk, small k, and instead of so this become sigma n equal to 0 to infinity xn e raised to minus xn minus j 2 pi by n into kn. This is the discrete Fourier transform representation. Normally, we will represent e raised to minus j 2 pi by n as wn. This is the representation for used for e raised to minus j 2 pi by n. So this can be also represented as sigma n equal to 0 to infinity xn wn raised to kn, small k, small n. So this is the representation of discrete Fourier transform. Yeah. The so I think that is enough for today. You got a glimpse of what a DSP processor is. What is DSP? It is continuation of signals and systems. And DSP means we are dealing with digital signals. So whatever we have converted using the sampling, using sampling, Nyquist sampling theorem and all, you have a digital signal which is stored as ones and zeros basically. So those digital signal, you are saving in your computer, and if you want to do some processing in that, okay, I could see some. Yeah. Okay, so in that case, we know that the signal is stored as digital data, and when you want to do some processing, say for example low pass filtering or high pass filtering, you don't need say RC components and all. You just need some delays and multipliers and adders. So we have seen that h equal to 1 plus at inverse is basically a low pass filter of first order. So this kind of higher order filters can be implemented using this kind of delays and multipliers and adders. Um, and you get or what all kind of processing of the signals can be done using these um, just multipliers, adders, and delay element. And afterwards, we'll be converting this digital data into back into the analog signal. So whatever the whatever we are supposed to do, say low pass filtering or high pass filtering or amplification, whatever it is, it happens in the it would have happened in the analog domain once you get back the original analog signal. So this is the basic overview of digital signal processing. And as I already told, DSP processors are widely used in many applications. In modern cars um, and automotive area, these DSP processors are used. They are used in say when you want to have some real-time applications like airbags and all. You use this kind of DSP process. Also, mobile phones, at least one mobile, at least one DSP core will be there in any mobile you take. There will be several other processors also, but DSP processor is something which we cannot avoid. So that's all about today's class. I think we can stop today's class. If you have any doubts, you can ask now. I think you are given some gap between each of the classes from this semester. So that will be convenient for you. So after each class, you will get a gap. And as I have told, we'll be having one online test based on this class before the next class in Moodle. So you can write that online test also. So we'll have as many online tests as many classes as we have. Like whatever the number of classes we have, that many number of online tests will also be there. Okay, so do you have any specific doubts or something? The syllabus and course plan, all these things I will upload in Moodle. You can check that. Yeah, so again, I welcome all you to the DSP class. So if you have any doubts or questions, you can ask now. Otherwise, we can stop today's class. Okay, so you can leave to the next class. Thank you.